So welcome. This is PHY 2048 Laboratory, and we're going to talk today about Boyle's Law lab. This is a dry lab because for some reason we couldn't get into the lab today. And what we're going to do is we're going to work with this equipment here. And the first part of it is just a plastic syringe. It's calibrated in, cubic centimeters. Actually, it's calibrated in milliliters, which is cubic centimeters. And I can open this up or close it and get a certain volume of gas. I'm going to connect this to a pressure sensor. It just screws into the side. And this pressure sensor consists of a little detector which measures the pressure and outputs a digital voltage signal. And then I connect the pressure sensor to a thing called a Lab Pro, and that's basically a analog to digital converter, so that we can then send this signal through to a computer, and the computer will take the measurements and display the reading and all this kind of stuff. And in truth, you can use the computer as a data acquisition system, and you can have the computer collect all the data and print the graphs for you and everything. Alternatively, you can use the computer as a digital recorder, and you can read the reading and then plot the graph and all that. There's advantages both ways. Today, we're going to use the computer as a digital reader. We're going to plot our own graphs. So we're going to trap a volume of gas inside the syringe, maybe 15 milliliters. It's at room temperature. And then we're going to study how the pressure of the gas changes as we change the volume. Now, as we change the volume, if we do it quickly, then the temperature is going to change. If I compress the gas, the temperature will go up. If I expand the gas, the temperature will go down. So we're going to wait until the syringe returns to room temperature and then take the reading, because we want to keep T constant. So we're going to basically look at the pressure versus the volume at constant pressure, at constant temperature. And this is basically, Boyle did this back in the day, probably 1670s, something like that. Yeah, probably 1670s. And this is part of our study of the ideal gas laws. So we're going to finish here and then we'll start taking notes. So let's make some notes. So we begin and we're going to say what our title is. This is lab, and it must be 13, 14, whatever it is on the particular semester. Look at the syllabus. And it is the Boyle's Law, belongs to Boyle, so it's Boyle's Law Lab. And as always, you're going to put the date down, and then you're going to put a page number on every page you write on, and every page you stick something on, you give it a number, just a sequential number, so you can refer to it easily. And then what's our objective for today? Remember, it's in our lab manual, it's in our lab report book, it's casual, we're just making notes for ourselves. Today, we measure the gas constant R and compare our value with the accepted value of, and it's going to be 8.3 joules per mole Kelvin. We will use the Boyles Law method. Now, we're not writing a lab manual, we're writing for our peers. And so if we say the Boyles Law method, they know what we're talking about because they've also done this course. So we're not explaining everything. We're writing to them as intelligent people, well-trained people as well. Okay. Please copy this page of notes. I forgot to record the audio. So let's have a look at the setup. So, oops, I need a pen. So we're going to have a gas cylinder. Let's draw the syringe. So this is my gas in here, and I can change the volume of the syringe. And then this is going to go immediately into a pressure sensor. So this is press sense. And what that does is it measures the pressure and sends out a voltage signal which is corresponding to the pressure reading. And this is basically a piece of electronic signal which comes out and we put into our digitizer. This is an analog system coming out and we want to digitize it. So we have this thing called the Lab Pro. And that enables us to digitize the thing. And then coming out of the Lab Pro, we go into our computer. I'm always struck by the computer. The symbol that I draw for a computer is very typical of a computer that is like 1980s, because that's when I started with computers. I keep wanting to put a floppy drive on there because, you know, computers have floppy drives. And this is running a program called Logger Pro. And on Logger Pro, we'd go to physics with vernier, and you'd look for Boyles Law Lab. And that actually is set up in such a way that you can actually plot the whole graph out that way. And what I found is that to some extent we need practice in plotting graphs out and analyzing them. It's the difference of, does the software run the lab or do you run the lab? My first year teaching in the States, on the first day the principal said to the entire faculty, one person will be in charge in every classroom and it needs to be the teacher. And in an experiment somebody's going to be calling the shots, and if it's not you, it's the computer program or it's the manual. And alright, it can start off being the manual, it should eventually be you, it should never be the computer program. So we'll take the numbers and we'll plot this thing out ourselves. Okay, so but that's the idea. This comes out and then we take our data, etc. So there's our setup. And then let me pause this. Now, one more thing on this is that I need to decide what amount of gas to begin my experiment with. And so before I connect the syringe to the pressure sensor, I'm going to move the handle of the syringe to set a certain volume. And the volume I'm going to set is 15 milliliters got to start somewhere. It's not the full capacity of the syringe, so I can pull on the syringe and make the volume a little bit bigger. And it's not as small as the syringe goes. The volume goes to 0 effectively. So it's somewhere in the middle. So, but I got to know what that number is, because that tells me how many moles of gas molecules are actually in the syringe to begin with. So let's set it up at 15 milliliters to begin with, and then you connect it to the pressure sensor. And then the other thing to realize is that this experiment is temperature dependent, and I'm going to try to maintain room temperature. And so I'm not going to hold the syringe by its body and pull. I'm going to hold the syringe by a little flap at the end so that I'm not touching the sides of the gas cylinder. And I'm going to be a bit patient. When I make a change, I'm going to maintain that change. I'll squish the gas and I'll hold it for a while. I'm not holding where the gas is. I'm holding the end of the syringe, and let the temperature of the gas get back to room temperature. And then I'll take my reading of pressure. Because if I take the reading of pressure too soon, I'll get the wrong value because the gas is not at room temperature. So wait for gas to return to room temperature before reading the pressure value on each reading. Cool. Okay. So we need to do a data table, and as always, data tables are numbered. This would be data table 1. Yeah, in our labs we tend to only have one data table. So you might say, who cares? But there will come a time when you're doing reports that might have 6 or 7 data tables in. And if you number them, it's much easier to write about them. And I'm a big believer that you write down what you see. Don't write down the SI units. Write down what you see, and then on paper do the conversion. Because if you write down the SI units and do the conversion in your head and you make a mistake, which we all do from time to time, there's no record in the manuscript saying, oh, but the original value was really so-and-so. You can correct it, but you've got to make an assumption about the correction. So I think it's much better, much cleaner, if we write down pressure. And we're going to record the pressure in the units that the system uses, it gives us, and it turns out that this system gives us numbers in kilopascals. Now Pascal is the SI unit, but kilopascal is 1,000 times bigger. Don't do the conversion, just make a column with pressure in kilopascals. And then the next thing I'm going to do is I'm going to measure my volume. Well, I'm going to set my volume, aren't I? So I'm going to have volume, and when I look at the syringe, I see milliliters, so write down milliliters. And then let's think. I want to have pressure in Pascal. Let me stop. I want to talk about this. I got 2 choices. I can change my units into SI units and plot that graph, or I can plot my graph in these units, and I can do a conversion at the end. For today, let's change the units. So we're going to talk about Pascal rather than kilopascal. And then for volume, I'm going to go to not milliliters, but meters cubed. I'm beginning to regret this already because there's an awful lot of math here. So let's do it the other way. I'm going to not worry about this. I'm going to leave them in their funky units, but I do need to plot 1 over the volume, volume. So I'm going to go 1 over volume, and the units will be 1 over milliliters. And then the next question you invariably get is, well, how many data points should I take? And again, that comes from the fact that you've been raised using lab manuals. And my answer is usually a bit flippant, and I say, as many as it takes. Not very nice, really. There's a joke, and that's, you know, well, you need at least 3 data points for a straight line graph. Let's talk about that. If I have 2 data points, I could draw a straight line through it, but I could also put a parabolic through. There's so many different curves will go through two data points. So okay, well, I can rule out that quadratic function by putting a 3rd data point in. So yeah, it is a straight line, but hold on, supposing it was cubic, that would work too. It's a bit unlikely. It's less likely to be cubic than it is to be quadratic. Well, okay, let's do 4 points then. Well, okay, so now it's either a straight line or it's a bit more of a funky function. I'm getting more and more weird functions as the alternative to the straight line. 5 would be better. So from a mathematical point of view, at least 3, 4's better, 5's better, you know. But then there's a whole other aspect to this, which is scatter. In a lot of physical systems, you're not going to get a beautiful line, you're going to get a range. And you're going to get something that has some scatter on it. And sometimes the way things work, is that a curve or is that scatter? And you can't answer that without taking more data points. So you say, well, maybe I could do with another data point in here. And oh, look, it went like that. Ooh, so is this just an anomalous point? I'm going to go outside that. Oh, look at that. Oh, now it's in the middle. Let's do some repeats. I try to repeat some of this, and pretty soon I'm looking at my graph and deciding where to take the next data point. And that requires that you are comfortable in plotting a graph before you finish collecting the data. And people say, how can you possibly plot a graph before you finish collecting the data? And the answer is, you say to yourself, from a physics point of view, what's going to give me the biggest vertical and the biggest horizontal value? And for this case, it's going to be when I have the smallest volume. So I go to the smallest volume and I measure the biggest pressure and I get a value, and I say, as long as my graph fits that value in, then if I make the volumes bigger from there, they should fit on my piece of paper. So a novice takes all the data and then plots a graph. Kind of works blind. Whereas it's like you're pitching and you close your eyes when you throw the ball. You've practiced and you know roughly where the batsperson is, but you close your eyes when you throw the ball. And you do it 7 times, then you say, oh, what did I do? Did I strike this person out? Whereas the alternative is you look and you say, oh, I'm going to go a fast ball, I'm going to do a slow ball, I'm going to adjust based on what I see. That's the more sophisticated way of doing this. And so it's a good idea in the lab to practice that methodology. So what we're going to do is we're going to take enough data and we're going to basically plot our data and we're going to see how we do. And we're going to stop taking data when we're satisfied with what we have. So I'm going to pause. I'm your lab partner now. And so I'm going to be the one who gets the data. I'm going to go and take the measurements. You're going to, if we had video, I'd show you moving the piston. And you could even read the values for yourself. But I don't have the piston here. I don't have the syringe here. So I'm just going to talk to you and tell you those values. I'm not going to write them down. And now I'm a teacher. I'm not going to write them down because I know that if I write them down, somebody's going to not listen to any of this and they're just going to look at the screen and write down everything I write down and then say, oh, look, I did the lab. And they've missed all this discussion. So I'm not going to tell you the numbers. I'm going to just talk to you about the numbers and very clearly. And then we're going to compare graphs and the like. So we'll go from there. So I'm going to stop the video, so you'd have to give me any time, but I need some time. So I want to talk to you just before we go about one last thing, and that is we're going to select the volume. And so what should we do? If we go to 1 milliliter, the volume will be incredibly small. It will be 1/15 of what we start off with. We're starting off at 15 milliliters. The pressure would be through the roof. I don't think physically we could even access that point. So there's going to be some ranges. We can't go beyond the end of the piston, which would be 20 milliliters. So we've got a scale on the linear graph from, well, it's 0 to 20, and we can't get down to 1. This would be milliliters. And so we can probably get down to 5, that I don't recommend it. So 5 to 20 is the kind of range where we can work. But then the question is, what do you do? Do you step linearly through that scale? And if you look at your final product, is going to be 1/V. That's changing it from a linear scale. And so even steps on the linear scale will not be even steps on the 1/V scale. And again, that's why it's a good idea to look and say, where am I having blanks in my graph and where am I having crowded points in my graph? But, this is old data. I'm going to come back in a second. Let's do initially something like 5 data points. And then we'll plot those. And then we'll come back and talk again. So these are the first 5 data points. So you can play this part of the tape over and over again. So for 5 milliliters, the pressure was 230 kilopascal. For 7 milliliters, the pressure was 210 pascal. For 10 milliliters, the pressure was 152 pascal. For 12 milliliters, the pressure was 123 pascal. And for 15 milliliters, the pressure was 105 Pascal. Kilopascal. They're all in kilopascals. So 5, 230, 7, 210, 10, 152, 12, 123, 15, 105. Plot me that graph. I'll do the same thing. So hopefully your graph can be compared with my graph. And let's have a look at what I did. So first of all, I looked at the value which gave me my biggest value for 1 over V. Let's get a pen on this. Pens. My biggest value for 1 over V, and that was the smallest volume, gives you biggest 1 over V, and it was 5 milliliters. My lab partner got a bit carried away, and that gave me 1 over 5 gives me 0.2, so that's that guy. And I knew we couldn't go any tighter than 5 milliliters, so that's going to be the top left, top right hand extreme for the graph. So from then on, everything's safe, everything's going to fit on. And then the other thing I'd point out is I am deliberately using a very convenient scale. You don't want to be caught with a horrible scale. So the value for this was about 230. So I went to 250. I said 1, 2, 3, 4, 5. There's 50. 1, 2, 3, 4, 5. There's 100. Whatever scale is convenient that goes over halfway up the page. So 1 for 1, 2 for 1, never 3, maybe 4 for 1, 5 for 1, never 6, never 7, maybe 8 for 1, never 9 for 1, 10 for 1, and so on. I did the same thing with the 1 over V scale, and the biggest number I'm going to get is 0.2, so I said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0.1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0.2. I'm over halfway across my page. I'm happy. Not trying to get all the way to the very side. Want a good scale, because if you have a very inconvenient scale, you'll make mistakes plotting the data points, and you'll make mistakes getting the slope. And then I plotted my data, and this is what my data looks like. And I'm a little bit concerned about a couple of things. Not a straight line. If you look at it, there's kind of a straight line. And then there's, you could call this a dog leg, couldn't you? It's kind of like that. And in some physical circumstances, you do get a dog leg like that. One physical mechanism dominates at the low end and another physical mechanism dominates at the high end. But the fact of the matter is that this could also be a problem with saturation of my amplifier. If I have a typical amplifier has a maximum voltage that it can put out, in effect it can't read more than a certain value. So it may be that that's the maximum output value for my pressure. And what's happened is that I just ran into, it's not a good graph there, just ran into it. Okay, I'd like to find that out before I go home. And so ideally what you'd do is you'd come in and you'd say, okay, I don't want to go above 0.2 because it's physically really hard to get to, but I can do maybe a couple of points here and here and here, and maybe a couple of points there, and maybe ironically go further away, expand. Let's have a look. I can go out to 20. 1 over 20 is 0.05, so I can go out as far as that. I can't access this bit here because my syringe doesn't go out that far. Okay, so maybe take a few more data points in here. Now, I'm using data from a real lab from a few years ago, and I wasn't part of the lab group, and you know, I'm not sure they've done everything I'd like, but I'm going to go back and look at the data, and I'm going to see what they did and come back and do some more work on this. So what I'm going to do is I'm going to stop, I'm going to look at the data, I'm going to read out some more data points, and then we'll add to this graph. Hi, I'm back. So 2 more data points were added. One data point is, I'm going to read them out now, so put them in the table. One data point was at 20 milliliters, and that gave a value of 85 kilopascal. And the second data point was at 8 milliliters, and that gave a pressure of 165 kilopascal. Now, it'd be nice to do some repeats, but the group didn't do any repeats. That's a pity. And it would be nice to look at the region where we think we're saturated, but because they took the data before they actually plotted the graph, they had no idea that any of this was going on. So 2 data points, 20 milliliters, 85 kilopascal, 8 milliliters, 165 kilopascal. Don't forget, you've got to convert your volumes into 1 over volumes. And so you have 2 more data points to add. Please make that adjustment to your graph, and then we'll discuss. So here's my next bit. If I can find a pen. Here's my next bit. And I've added a couple of data points from when comparison with previously. Let's get a pen. So I've added a data point down here, and I've added a data point here. As I say, it would have been nice to look in here somewhere. I can't go beyond this line, and I can't go beyond that line, so I'm like spanning the region. It's not bad actually, there's reasonable steps in there. So the next thing I have to do is I noticed that I'm using point protectors. I'm proud of my data points. I want people to be able to see them. And I'm not trying to hide where the points are. I'm using these circles so that in 20 years time people will see that's a data point. That's not an ant that squished in there. That's a true data point. And then my next job, I'm gonna kind of show you where I'm going to go with this. I look at this and I see scatter. I don't care about where are we? I'm gonna not worry about that point there. Okay. I'm going to put my ruler. I'm going to approach from the underside. Whoops, daisy, I'm going off. And I'm going to try and line up on these guys. As I say, I don't worry about that point there. I'm going to put down anomalous point, possibly saturated. And then that's going to give me one slope. And then I'm going to look on this side and get another slope. I'm not going to worry about going through the origin. I'm going to draw my lines down there, but the origin is not a data point. You can't force it through the origin. It's a test. It's not a data point. So I'm going to draw those 2 lines. I'm going to remember how we do this. We look for a very nice point where the cross of the grid matches the line, and where's another good point? There. The cross of the grid matches the line, and then I'm going to read and write down the number for that guy. I'm going to read and write down the number for that guy, and they should be easy because they're on the actual lines. I'm going to read and write down the number for that line. I'm going to read and write down the number for that line. I'm going to write down my rise and my run, and I'm going to work out what my slope is, and this is going to be my lowest reasonable slope. And then I'm going to look along this second line again for where the cross of the graph paper just lies on the line that I've drawn. And I'm going to look for another point where that happens. There's a nice point where that happens. Write down the data, write down the number, write down the number, write down the number, write down the number, write down the difference, write down the difference, work out my highest reasonable slope. If you write all those numbers down, you won't make a mistake and everybody will follow what you're doing. If you cut corners, you'll make mistakes and people won't be able to follow what you're doing. So just write down the numbers. It's not a big deal. That's my next job. I'm going to go away and do that on this thing. I want you to do it on yours. And then we'll compare slopes. We might not have the same slope because we're going to draw our own individual lines, but we'll have decent numbers. And then we'll talk about what that means. Okay? So that's the next thing we're going to do. So this is my third look at my graph, and I've added on my slope lines, and I wrote down the value there. It's easy to get because it's on a line. I wrote down the value there, and I took the difference between the two, which is 0.17. The flashlight didn't show up too well. I wrote down the number here and wrote down the number there and wrote down the difference. So I'm being clear with whoever reads this. If they know what they're doing, they can get all the information and check my work really easily. Same thing with this top line. I picked a point there and wrote down its value, picked a point there and wrote down its value, and then did those two and did the differences. And then because this is a working document, it's not a picture, it's not pretty, I actually even was able to work out the lowest reasonable slope, simply taking the 180 divided by 0.17, and I got 1059 kilopascals per 1 over milliliters. And for the highest reasonable slope, I was able to get a value of 1385 kilopascal divided by 1 over milliliters. So this is an instructive document. People looking at this will be able to figure out an awful lot about what I did. When people get other people's data, they strip it. They look at the lines and they do their own gradients and they say, well, I prefer this line, and they reanalyze it. I didn't put any comment in about this point, and that was a mistake. That was an oversight. And I would put down here, I don't know how to spell it, anomalous, al-o-u-s point, letting them know that I didn't forget it. I deliberately ignored it. And I'm going to put down here P detector saturation, and then question mark, because I don't know it's that, but I think it's that. I thought a comment like that I think would be very useful. Okay. And then the next thing I'd like to do is take these two slopes and do a calculation based on them. And that's what we do next. So welcome. Let's get a pen and let's do our calculation page. And there's a fair number of calculations we need to do on this one. Let's transfer across first of all our highest reasonable slope equaled, and it was 1385, and we looked at the axes and it was kilopascal over 1 over milliliters, cubic centimeters. And our lowest reasonable slope from our graph was equal to 0, it was 10, wasn't it? I got it written down here somewhere. Yeah, 1059 kilopascal per 1 over milliliters. Just to be clear, so this equals 1385 kilopascal milliliters, because 1 over 1 over milliliters is milliliters. And this equals 1059 kilopascal milliliters. That's important to recognize. And then let's remind ourselves what we're saying is that our value of R is equal to our slope over NT. And I suppose the first thing I'd like to do is get those slopes into standard units, because they're not in standard units now. So let's say our highest reasonable slope is equal to 1385. And the way I do this is I use factor label technique. So this is kilopascal milliliters, and I say, but I don't want it in kilopascal, I want it in pascal. So I put kilopascal on the bottom and pascal on the top, and 1 kilopascal is 1,000 pascals. So I can get rid of that bit. And then I say, oh, but I'm still in milliliters. And I want to go to SI units. So I want to be in cubic meters. And I remember that a milliliter is 1 cubic centimeter, which is 1 centimeter by 1 centimeter by 1 centimeter. So I want to get rid of milliliters and I want to have meters cubed. And I know that, doesn't matter which way around I do it, 1 meter cubed is 100 times 100 times 100 centimeters, which is 10 to the 6 milliliters, cubic centimeters. So highest reasonable slope is equal to 1385 times 10 to the, well, there's 1,000 on the top and 1,000,000 on the bottom, so it's 10 to the minus 3. And the units will be pascal meter cubed. And I don't need to do this math again. I can say my lowest reasonable slope is equal to the original number, which is 1059, again, times 10 to the minus 3 pascal meter cubed. Cool. So that's that bit. Let's put that in a little box. And so then the next bit is, let's do the temperature. I measured the temperature in the room, and the temperature equaled 22 degrees C, which equals 295 Kelvin, and I need to be in Kelvin. Now, is the temperature of the gas inside the syringe 22 degrees? I hope so. If we didn't let it cool down enough, if it was a higher temperature than we think it is, then basically this T is higher than we think it is, which means our R value will be lower than it should be. Can you see T's on the bottom? So if T is bigger than we think it is, then R that we get will be smaller than we think it is. So we get a value that's too small. And then the next bit is we've got to work out our N. Now, value of N, the number of moles. Well, let's have a look. The amount of gas that we put in was 15 milliliters. So let's start with that. And the trick I'm going to use is that 1 mole of gas at standard temperature and pressure equals 22.4 liters. It occupies 22.4 liters. So ironically, I want to get the liters. So, oh, that's not so bad. I want to get rid of the milliliters and I want to have liters, and I know that 1 liter is 1,000 milliliters. So I got rid of that. Can you see how the factor label method, this method of using this trellis, is really kind of friendly because you can think as you go along. So now I've got this in liters. Oh, of course. And I know that there's a relationship between the number of moles and the number of liters. I only need L. And the chemists tell me, or maybe I just learned it in chemistry, that 1 mole of gas occupies 22.4 liters at standard temperature and pressure. And I'm close to it. I'm not, might not be perfect, but I'm close to it. So again, the liters goes away. And so this gives me the value. Now, you know, before I started writing, I didn't know what I was going to write. I just worked through it. So that's the value of good layout. And so when I put these things through, I've calculated this previously. I'm not sure I can find it actually. Let's have a look. So 15 over 1,000 times 24, and this came out to be 6.696 times 10 to the minus 4 moles. Now, do I need all those decimal places? You know, we'll look at our answers at the end because we're going to get an envelope, a spread of answers. So just let the numbers run on until you get to the end. Okay, so that's where we're at on that. So now, our highest reasonable R is equal to our highest reasonable slope, because it's on top, over, and we don't have a variety of n, so we're going to put down n, and we don't have a variety of t, so we put down t. If we want to be really picky, we could say, well, the temperature could be as big as 22, or maybe as small as 21, and we could have a little variation there. And maybe n, well, maybe we had 14 milliliters rather than 15 milliliters. So we could have some variation in these two, in which case we take the highest reasonable slope, the lowest reasonable n, because we want the biggest answer, and the lowest reasonable t. And we want the lowest reasonable r. We'll take the lowest reasonable slope and the highest reasonable n and the highest reasonable t. But we're going to leave it for today. We're going to do it like this. So then this equals my highest reasonable slope. I'm up here. 1385 times 10 to the minus 3. And then I divide this by 6.696 times 10 to the minus 4. That's my n. And also I divide it by 295. And when I put those numbers in, I just worked this out a minute ago. This was 7.011, and let's have a look. The units would be, well, let's have a look. My slope was in, I'm sure I have it down somewhere. My slope is in Pascal meters cubed, and then I'm dividing this by n, mole, and then Kelvin. So it's Pascal meters cubed over mole Kelvin. And let's think about this a little bit longer. A Pascal equals a Newton per meter squared, and I take newtons per meter squared and multiply it by meters cubed, so I get Newton meters, and a Newton meter is a joule because of work. So I got a variety of units I could have in here, and the simplest one to put down is the joule. And I think that's what we quoted our original answer in when we started off, when we said the accepted value. It's the same thing, the actual. That's why we talk about dimensions as opposed to units. Dimensions are fundamental. Units, depends where you get tired of doing it. If I look over here at the lowest reasonable R, that's my lowest reasonable slope over NT, which equals, I'm actually running out of time, so I can only put up an hour's worth of stuff. So this is going to be 10, 5, 9 times 10 to the minus 3 over 6.696 times 10 to the minus 4 times 295, which of course is on the bottom, which gives us 5.361 joules per mole Kelvin. Cool. The accepted value, R accepted, is equal to 8.3 joules per mole Kelvin. So I'm not actually in, I'm a little bit lower than I expected. And that might be I didn't wait long enough. My temperature was higher than I think it is. That's an interesting point. Let's do this, just this last little bit. I've got just 4 minutes. Let's do a comparison diagram. I want you to commit to, did you agree or did you not agree? And the way that I do this is I put down my 3 numbers. So I have 7.011 and I have 5.361 and I have 8.3. So we draw a box and we use a decent scale. So let's make this 9 and then 1, 2, 3, 4, 5, 8, 1, 2, 3, 4, 5, 7, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 5. So I do a linear scale, nice and steady. And this is my value of R in joules per whatever it was. It was mole K. And I have 2 columns in here. I'm rushing a bit, I'm sorry. I have 2 columns. I have EXP, experimental, and ACC, accepted. And the accepted is 8.33. So you actually can use the scale. You can get it very decently, 8.3. And then the experimental is 7.01. Oh, we're actually a fair bit out, aren't we? And 5.3. Now, what I said was that the highest reasonable value was 7.011 and my lowest reasonable value was 5.361. It's unreasonable to be bigger than this. So I don't agree. And that's the way it is. My job is to do the experiment right, and the results are the results. Don't get tempted to kind of fiddle the results. Just accept it. So the conclusion is the measured value of R was between, let's say 5.3 and 7.0 joules per mole K. This is not consistent with the accepted value of 8.3 joules per mole K. Now, in a discussion section, we could discuss why, and you could say, oh, temperature was wrong or whatever. But that's for a further development. My job is to report what I did as I did it, as professionally as possible. And it wasn't perfect. There's some issues here. Don't cover it up. Just write it clearly. And then the employer can turn around and say, can you go back and readdress this? don't be cornered by the fact that your answer doesn't agree with what you expect. You may have discovered something that's exciting. There's the write-up, please. Can you do me a favour? I want to just see if people are listening. So at the end, I'd like you to write down, physics is fun. Last thing you write down is physics is fun. Okay? Do me a favour, write that down. I just want to see how many people put it down. That's it. Good luck, lab partner. I'll see you next time, and we'll see how it goes.